Hello students, in this lecture we will see the next point, that is current density equation. In solids, the charge carriers may move in random motion. So at room temperature, the random motion of the electrons is visualized as the scattering of the electrons with the impurities and the lattice within the solid. So when we consider the group of n number of atoms, then there will be a no preferred direction of the charge carriers due to the random motion of individual electrons. So due to this random motion of n number of electrons, there will be no preferred direction, and if we consider the motion per centimeter cube, then there is no net motion of these electrons. So if we consider or take this random motion, if this is the starting point, then the electron will move in this direction. After scattering, it will move in this direction, again in this direction, again in this direction, again in this direction, again. So in this way, the charge carriers in the solid will move in the random motion, and there is zero net probability to reach these electrons at the starting point again. So if an electric field epsilon x is applied, so I will denote this as a figure 1a, and if the electric field is applied in positive x direction, this is the direction of applied electric field, then due to applied electric field, the charge carriers within the solid experience the force, and which is in negative x direction, and the velocity Vx in this case is given by minus mu n into epsilon x. So this is figure 1b. So due to application of electric field in positive x direction, the electron will experience the net force, which is minus q. F is equal to minus q into epsilon x, which is due to the application of electric field in positive x direction. So this force may be insufficient to alter the appreciable random path of individual electron, and the effect when averaged over all the electrons, then a net motion of group of n number of atoms will make motion in negative x direction. So if we consider Px will be the momentum experienced by the electrons, or Px will be the x component of momentum of the group of n number of electrons, then the force of field on n number of electrons per centimeter cube is given by minus nq into epsilon x, which is equal to dpx by dt. So this is equation number 1. So from Newton's second law of motion, one may say that the force is nothing but time rate of change of momentum, and here as for individual electron, the force experienced due to the application of electric field is minus q into epsilon x. So for group of n number of electrons, one may write minus nq into epsilon x is equal to dpx by dt at field due to applied field. So initially this equation indicates continuous acceleration of the electrons in negative x direction. That is, due to application of electric field in positive x direction, the electrons will experience the acceleration in negative x direction. The net acceleration given by the equation number 1 is just balanced by the steady state of deceleration of electrons by collision process. Thus, the steady state field epsilon x does produce net momentum, which is p minus x, and the net rate of change of momentum when collision is included must be 0 in the case of steady state current flow. So to find the total rate of change of momentum from collision, we must investigate the collision probabilities more closely. If the collisions are truly random, there will be a constant probability of collision at any time for each electron. So let us consider the group of n0 number of electrons initially. So after time t, the number of electrons which undergoes the collision is given by n of t. So at time t is equal to 0, there will be n0 number of electrons, and after time t, n of t will be the number of electrons which undergo the collision process. So the decrease in n of t at any time t is proportional to the number of electrons that left unscattered at time t. So one may write minus d n of t by dt is equal to 1 upon t bar into n of t. So this is equation number 2, in which t bar inverse is proportionality constant. Proportionality constant. And this equation number 2 has the solution, which is exponential function. So the solution of this equation is given by n of t is equal to n0 into e raised to minus t upon t bar. So this is solution of equation number 2, in which this t bar is nothing but the mean free time, or it is called as mean time between the scattering events. So the probability that any electron has a collision in time interval at in a time interval dt, that is the probability at for any electron has collision in time interval dt is given by dt upon t bar. So the differential change in px due to the collision in time dt is given by dpx, which is equal to minus px into dt upon t bar. So this is next equation number 4. The rate of change of px due to deceleration effect of collision is given by dpx by dt is equal to, as this time rate of change of momentum is due to collision, so I write here dpx by dt collision is equal to minus px by t, minus px by t. So this is next equation number 5. The sum of acceleration and deceleration effect must be 0 for steady state. So taking sum of equation number 5 and equation number 1, we may write minus px by t minus n cube epsilon x is equal to 0. So this is next equation number 6. The average moment per electron is given by average of px is equal to px by n, and from this equation number 6 we may write px by n is equal to minus q into t into epsilon x. So this is next equation number 7. So as expected for the steady state, this equation number 7 indicates that the electron have on the average a constant net velocity in negative x direction. So we may write the average velocity, average of Vx is equal to average of Px upon Mn star, and which is equal to which is equal to minus q into t bar into epsilon x upon Mn star. So this is next equation number 8. Actually, the individual electrons move in many directions by thermal motion during a given time period. But this equation number 8 tells us that net drift of an average electron in response to electric field and the drift speed described by this equation number 8 is much smaller than the random speed due to thermal motion. So the current density resulting from this net drift is just the number of electrons crossing unit area per unit time, and which is given by n into average of Vx, and which is multiplied by the charge on the electron, which is minus q. So the current density of the electrons in the solid is given by J is equal to minus q into n into average of Vx. So this is next equation number 9. So using equation 8 for average velocity, we get Jx is equal to minus n q square into t bar upon mn star into epsilon x. This is equation number 10. Thus, the current density is proportional to the electric field. As we expect from the Ohm's law, we may write Jx is equal to sigma into epsilon x. So, comparing these two equations, we may write sigma is equal to, here is plus, so sigma is equal to n q square t bar upon mn star, and this sigma is nothing but the conductivity. So these are equation number 11, and the conductivity can be written as sigma is equal to nq into mu n. So by comparing these two equations of conductivity, we may write mu n is equal to q into t bar upon mn star. So this is equation number 12. The quantity mu n is called electron mobility. The mobility defined by this equation number 12 can be expressed as average particle drift velocity per unit electric field. So comparing this equation number 8 and equation number 12, we get mu n is equal to mu n, which is equal to minus average of Vx upon epsilon x. So this is equation number 13. The minus sign in equation number 13 results in the positive value of mobility, since electron drift opposite to the applied electric field. The current density can be written in terms of mobility as Jx is equal to Jx is equal to Qn into mu n epsilon x. So this is equation number 14. So this equation number 14 derived by assuming that the current is carried primarily by the electron. For whole conduction, we change N to P and minus Q to plus Q and mu N by mu P, where this mu P is Vx by epsilon x. Mu P will be average Vx by epsilon x, and this mu P will be the mobility of holes. If both, that is electrons and holes, participate in the conduction, then this equation 14 for the current density will change into Jx is equal to Q into N mu N plus P mu P into epsilon x. So this is equation number 15, and this equation number 15 gives the current density equation for which both, that is electrons and holes, take into participation in the conduction process. So with this I will stop here. Thank you.